Let's design a URL shortener. Turn a long link into a short one that resolves back correctly forever. Bitly's normal redirects run through their main service, but they also built a completely separate backup that reads straight from S3 and kicks in automatically if everything else goes down, so a link still resolves. That's a lot of engineering for what looks like a simple lookup table. The obvious plan, one table, one mapping, done. But traffic tells a different story, roughly 100 redirects for every link created. The right side was never the hard part. So where does the real problem live? Two groups of requirements to settle before any architecture gets sketched. On the functional side, a user submits a long URL and gets a short one back. Anyone holding the short link gets redirected to the original destination. The owner of a link can update where it points. The owner can also revoke it, so it stops resolving entirely. For verbs, nothing more. No search, no folders, no team sharing. On the non-functional side, the redirect itself needs to complete inside 10 milliseconds at the 99th percentile, since a slow redirect defeats the entire point of shortening. Durability means a link resolves indefinitely once created, through partial infrastructure outages included, not only under normal operating conditions. Bitly itself commits to a 99.9% service level target with round-the-clock monitoring, which sets a reasonable bar here too. Consistency can be eventual, specifically on the redirect path. If an owner updates where a link points, propagating that change everywhere within a bounded window is acceptable, as long as the bound is explicit. And the ratio assumed throughout is 100 redirects for every one link created, the single most important number in this design. Equally important and deliberately excluded. Click analytics, since nothing here should compete with the read path this design exists to protect. Custom vanity domains, which would add a DNS verification surface no stated requirement implies. QR code generation, a presentation layer feature orthogonal to the four verbs above. Link expiration scheduling, a different requirement than resolving indefinitely until revoked. Any moderation beyond the automated safety check at creation, and bulk or programmatic link creation at onboarding scale, a separate, low-volume control plane concern this design doesn't touch. 100-to-1 read-to-write ratio already tells us where this design lives or dies, on the read path, not the write path or storage. Let's confirm that with real numbers. Start from 500 million monthly active users. About 10% are active on a given day, 50 million daily active users. Of those 50 million, only a slice ever creates a link on a given day. The assumption here is one link per user roughly every 50 days, which works out to 1 million new links every day. Divide by the 86,400 seconds in a day, and that's about 11.6 writes per second on average. Multiply by 2 to cover the daily traffic peak, and that's 23.1 writes per second at the top of the curve. Redirects run at 100 times that rate, given the read-to-write ratio already established. Multiply the average write rate by 100, and average redirects land at 1,160 per second. Double that for peak, and the busiest moment sees 2,320 redirects a second. Each stored record, the mapping itself plus its metadata, runs about 500 bytes. 1 million new records a day at 500 bytes each is half a gigabyte of new data daily. Carry that forward 5 years, and total storage lands around 912 gigabytes. Translated into bandwidth, that's a fraction of 1 megabit per second inbound, and a little over 5.5 megabits per second outbound. Bandwidth was never going to be the constraint. Writes at 23 peak per second could run on a single modest node. The actual bottleneck sits entirely on the read side. 2,320 lookups a second, served consistently fast enough that a redirect feels instant. That number is what the rest of this design answers to. That 2,320, though, is an average spread across every key in the system. A single link drawing even 5% of peak traffic, plausible for anything that goes viral, concentrates over 100 requests a second onto one record, not spread across the dataset. Averages hide this entirely. A design sized only to the aggregate number can still fail on the concentrated case, which is exactly the number the caching decision has to answer to, not just the peak. For endpoints capture every decision worth discussing. Creating a link is a post to /URLs, taking the long URL in the body and an idempotency key in the header. The key matters because a client retrying after a timeout should never mint two different codes for the one link it meant to create once. Resolving a link is a GET to the shortcode itself. It requires no authentication at all, and it responds with a redirect rather than a body. Updating a link is a put to /URLs followed by the shortcode, authenticated as the owner, changing only the destination URL. Revoking a link is a delete on that same path, also owner authenticated. After that, the code stops resolving for good. Every write-side call belongs to the owner. Every read-side call belongs to the world. Start simple and name every box as it earns its place. A client calls the API through a load balancer, which fans requests across a stateless fleet of API servers. Stateless, because state living anywhere in this tier would defeat the point of adding or removing servers freely under load. On the create path, the API server runs the submitted long URL through a synchronous safety check before anything is persisted. Consider the alternatives first. Skip scanning entirely, and at 1 million links created a day, even a small fraction turning out malicious compounds into a meaningful number of live phishing redirects, riding this platform's own reputation. Scan after the link is already live instead, and there's a window, however short, where a bad link is already shareable, across up to 2,320 peak redirects a second. A guarantee that a link resolves indefinitely doesn't distinguish briefly live from permanently live once it's been shared even once. So the check runs once, synchronously, on the right path, before the code is ever made resolvable, the same point in the flow where X's own TDCO scans every link posted to that platform. The cost, a domain that turns malicious after approval slips through until the next periodic rescan. Accepted, because catching it on every redirect would multiply the check by the full 100-to-1 read-write ratio. After the check passes, the server generates the shortcode and writes the mapping durably. State for this entire system lives in exactly one place, that durable record, never in the API tier itself. On the redirect path, the server checks a cache first. A hit returns the destination immediately, and a miss falls back to that same durable store. Both paths always agree because they read and write the identical record. Bitly survives total data center outages with a failsafe redirect path. X's T.co scans every link for malware before redirecting. Both reveal the same read-heavy, failure-isolated architecture this interview actually tests. The next two sections build exactly that. First the data store and the code itself, then the caching and failure isolation layers sitting in front of it. Walk the redirect end to end. The load balancer adds roughly a millisecond, the API server another 2, and a cache hit resolves in about 3 more. That's 6 milliseconds spent against a 10 millisecond budget, 4 milliseconds of margin before the request ever has to touch the data store at all. 5 things can break this design, and everything from here forward exists to close one of them. The mapping itself might not durably persist. The public code might be walkable by a scraper. A single link going viral might saturate whatever serves it. A malicious destination might ride the platform's reputation. And the primary stack itself might go down entirely. This section and the next close the first 3. Failure modes closes the rest. This data model has one entity, the link record. Short code, destination URL, owner, timestamp, revoked flag. No click log, no analytics, already ruled out of scope. where that record lives. Every read and write is a single key lookup by short code. No joins, no range scans, no secondary index, ever. A relational engine would serve that lookup fine. Indexed point reads are exactly what Postgres is good at. The reason to skip it anyway, every one of its real differentiators, joins, multi-row transactions, referential integrity, goes unused here, and a self-run primary has a harder time surviving a full regional outage than the alternatives. A cheaper alternative worth naming honestly, raw object storage, at a fraction of managed key value pricing for a dataset this size, since these records are written once and read far more than they're ever rewritten. The catch is exactly what a managed store avoids. Object storage latency doesn't clear 10 milliseconds on its own, so this choice only works if the cache ahead of it is treated as load-bearing, not optional. This is the shape Bitly actually runs in production, but only for its last resort failover path, reading straight out of S3, specifically because that tier accepts slower, degraded service in exchange for surviving a total outage. Bitly's everyday redirect path runs on separate, faster infrastructure. Object storage is a legitimate choice for a team pushing cost lower and comfortable leaning harder on the cache, not evidence that object storage is how this shape of traffic gets served day to day. A managed key value store, DynamoDB or Cassandra, is the winner. Purpose-built for exactly this access pattern, with near-zero operational overhead, and its typical single-digit millisecond latency clears the 10 millisecond redirect target directly, without depending on the caching tier ahead of it to make that number work. Records are created once and almost never mutated, so its replication tuning and tunable consistency aren't earning their full keep here. A real cost, just not a decisive one, since a managed service runs this workload without strain either way. Why not fold this into caching? Because a cache can lose every entry on restart with zero correctness impact. That's the point of a cache, while the durable store's job is surviving that exact restart. Now, the shortcode itself. Generate one fast enough for 23 peak writes a second in 6 to 8 characters. A raw auto-incrementing counter, base 62, encoded, looks solved, until the code is public. Given a plain counter as the code, how fast could someone read back every URL created today? At 1 million codes a day, an attacker at 1,000 requests a second walks the whole day's counter in under 17 minutes, reading back every long URL behind it. Hashing the URL and truncating to 7 base 62 characters swaps one flaw for another. Expected collisions run near 473,000 across this system's 5-year total routine, each one forcing a right path retry. A full UID costs 22 characters, no longer short. Twitter's Snowflake coordinates tens of thousands of IDs a second. Complexity this system's write volume doesn't justify. What survives? Instagram's approach. A timestamp, shard ID, and sequence composed into one integer, generated locally per shard with no coordination. Instagram's version runs 64 bits, needing 11 characters, 3 more than this system can spend. Shrinking the same idea to 46 bits, 30-bit timestamp, 8-bit shard, 8-bit sequence, fits 8 characters, with headroom past the 23 peak writes needed. Never expose that raw sequence. Run it through a reversible permutation, then base 62. Encode it, a bijection, so uniqueness survives while sequential order doesn't. An interviewer will ask, if reversible, isn't that just obfuscation? Correct. It defeats a scraper walking sequential codes, not an attacker reverse engineering the permutation. A rotated key closes that gap further if the threat model demands it. Here is the number the entire read path answers to: 2,320 redirect lookups every second at peak, against a data store built for durable point reads, not necessarily built to survive that request rate at low latency indefinitely. Before anything changes, every one of those lookups goes straight to the object store. Survivable at today's scale, but with zero headroom the moment a single link goes viral and a large share of that traffic concentrates on one key. What changes? A distributed cache sits in front of the data store, and every redirect checks it first. Why not skip the cache and serve every lookup straight from storage? Even a single well-provisioned node nominally handles 2,320 peak reads a second, but it leaves zero headroom for a hotkey spike and ties redirect latency directly to storage load. Why not an in-process cache per server instead of a shared one? Spread across a fleet of, say, 20 API servers, that peak splits to roughly 116 requests per server. A moderately popular link has to warm up independently on every single server rather than once, and any server that restarts starts back at zero. Why not lean on CDN edge caching alone? A CDN caches per edge location with no single invalidation call. Updating one of only 23 peak writes a second worth of links can still leave stale destinations resolving at other edges for a full cache window, with no application-level hook to clear it immediately. What wins? A shared distributed cache tier with a client-side routing layer in front of it, the same shape of architecture Pinterest runs in production, where a comparable tier serves on the order of 180 million requests a second across a dataset in the hundreds of terabytes. That's several orders of magnitude past this system's own 2,320 peak, which is exactly the point. The pattern has enormous headroom at any scale smaller than the one it was proven at. This is the same partitioning problem consistent hashing solves for Dynamo-style stores. Cache shards stand in for ring nodes, short codes stand in for keys, and losing one shard only holds that shard's keys, not the whole cluster. That single hot key, drawing 116 requests a second, sets up a different failure than raw capacity, the thundering herd, sometimes called a cache stampede. If that key's entry misses at the same instant for 100 concurrent readers, all 100 would normally fall through to the data store together, turning one popular link into a burst indistinguishable from an attack. The fix, already built into this cache tier, is request coalescing. The first miss for a key triggers the actual data store read, and every other concurrent request for that same key waits and receives the same result once it lands, instead of issuing a read of its own. One request reaches the data store, not 100, no matter how many readers converge on the same expired key at once. An update just landed on a cached link. What's the very next action? An interviewer will ask the obvious follow-up. What happens when a link is deleted or its destination changes? Cache-aside handles it. The update hits the data store first, then explicitly evicts or overwrites that key's cache entry, rather than waiting on a time to live to expire on its own. The cost: bounded staleness, not perfect consistency. Acceptable since updates are rare against overwhelmingly read-heavy traffic, with the time to live as backstop for a missed eviction. After this change, the data store sees only cache misses, a small steady trickle instead of the full 2,320 peak, and the number that opened this section stops being a threat. Before picking a winner, here's how every real candidate stacks up on the axes that actually matter: access pattern fit, operational overhead, and whether each one clears the 10 millisecond read target on its own. We chose a managed key value store over a relational or NewSQL database. What we gave up is ad hoc queries and joins. Listing every link by owner needs a purpose-built index planned in advance, not an arbitrary query against the table. This is acceptable because the stated requirements are single key create, read, update, and revoke only. We'd revisit this the moment analytics or listing queries become a real, recurring requirement. We chose a reversible permutation over sequential IDs to stop enumeration. What we gave up is cryptographic-grade security. Someone who reverse engineers the permutation could still enumerate every code. This is acceptable because the realistic threat is an automated scraper walking sequential numbers, not targeted cryptanalysis. We'd revisit this if scraping attempts outpace the key's rotation cadence, or shard coordination needs exceed the 8-bit shard budget. We chose a cache-aside tier over always reading fresh from storage. What we gave up is perfect consistency. A redirect can serve as stale destination for up to the cache's time to live if an eviction is missed. This is acceptable because link updates are rare against a 100-to-1 read-heavy workload. We'd revisit this if that ratio drops well below 100-to-1 or strict read-after-write consistency becomes a hard requirement. We chose to run a second, deliberately minimal serving path for redirects. What we gave up is a simpler operational picture, one more service to deploy and keep in sync with the primary data store. This is acceptable because the alternative is a redirect path that dies with the rest of the stack, breaking the requirement that a link resolves indefinitely. We'd revisit this if the durability bar itself relaxed enough that outages became acceptable. We chose to scan a link once, at creation, rather than on every redirect. What we gave up is coverage of a destination that turns malicious after it was already approved. A compromised domain slips through until the next rescan. This is acceptable because catching that case on the read path would mean paying the check on 2,320 requests a second instead of 23. The gap closes instead through a periodic rescan against already issued links. We'd revisit this if compliance ever required continuous, not just creation time, monitoring. The most severe scenario, the primary application stack or an entire data center, goes down. Detection is a health check away. Timeouts to the primary tier exceed threshold, and monitoring flags failed health checks across the whole serving path. Without isolation, every redirect fails with it. The full 2,320 peak reads a second, and the 23 peak writes alongside them drop to 0, directly breaking the requirement that a link resolves indefinitely. A single tier serving both writes and redirects has nothing to fall back on. Active-active replication across regions protects the data, but not the serving path in front of it. A bad deploy can take that path down in every region at once, while the data itself stays healthy. Every region of the primary stack is down. What's the one thing that still has to work? What survives? A standalone, deliberately minimal service reading redirects directly out of durable storage, reachable by retry on timeout or by DNS pointed straight at it. If a data center is unreachable, the pattern bitly runs in production. Doesn't a second serving path just double the operational surface? Not really. It skips almost everything the primary path does. No safety checks, no write traffic, just a lookup and a redirect, which is exactly why it keeps serving through a failure that has taken everything else down. There's a name for the alternative this section just ruled out, a single point of failure. Route both link creation and every redirect through one application tier, and that tier's outage doesn't just slow writes down, it takes the read path with it, the exact path the durability requirement exists to protect. The standalone failsafe path removes precisely that dependency, a separate, deliberately minimal service reading straight from durable object storage, sharing no code and no infrastructure with the primary stack. The primary tier can fail completely, and this path keeps resolving regardless. That is what eliminating a single point of failure actually buys, not a vague sense of extra resilience, but one specific dependency removed from the one path that cannot go down. One clarification, the API tier, drawn as a single box throughout this video, is already a fleet of instances behind the load balancer. Losing any one of them costs nothing. A fleet doesn't close the gap the failsafe exists for, though. A bad deploy or a regional outage can take every instance down at once, correlated, not one at a time. a different failure shape than what redundancy inside one tier solves, which is exactly why an independent path matters, not just more copies of the same thing. Recovery is uneventful. Normal health check routing shifts traffic back once the primary stack recovers, and no data was ever at risk, since both paths read the same, durably replicated record. A second, more common scenario, the cache tier degrades. A node lost, or a large share evicted at once. The signal is hit rate dropping below baseline, alongside rising P99 latency. Reads fall through to the data store, add up to the full peak, but cache aside with graceful fallback means a request only slows down, it never fails, and the cache rewarms on its own as normal traffic returns. A third scenario looks nothing like either of those. No node goes down at all. A shard misconfiguration mints a colliding code. A leaked permutation key lets a scraper walk what looks random but isn't. Neither shows up as a health check failure. The service stays up throughout. The signal is different, too. Duplicate codes for different records, or a spike in near-sequential requests. The fix mirrors the signal. Validate shard assignment against a central registry at startup, and rotate the permutation key the moment exposure is suspected. Already issued codes keep resolving either way, since the stored mapping, not the key, is what a redirect actually depends on. There's a name for the correct choice when that reputation check itself goes down. Fail closed, not fail open. If the dependency being unavailable meant skipping the scan and letting the link through anyway, that's failing open, and it reopens the exact phishing risk this check exists to close. Failing closed means creation requests queue or reject with a retryable error while the dependency is down. Nothing gets to skip the check just because the checker is unreachable. A short-lived cached allow or deny result for recently seen domains absorbs brief blips without forcing every request through that closed door. Nothing so far stops a script from hammering this endpoint faster than any real user would. The fix is a token bucket at the edge. Tokens drip in at a fixed rate, and every creation request spends one. An empty bucket doesn't queue the request or slow it down. It bounces it immediately with a 429 before it ever reaches the load balancer or consumes an API server thread. At 23 peak writes a second, this bucket barely notices real traffic. It exists specifically for a caller replaying requests far outside that shape. There's a category of failure that isn't architectural at all, a bad deploy, a mistakenly flipped feature flag, an accidental cache flush during routine operations. In practice, this category causes more incidents than every hardware or dependency failure covered so far, combined, because every other safeguard in this design assumes the software is doing what it was built to do. Detection is the same signals as everything else. Hit rate drop, error rate up, latency spike, correlated against a deploy timestamp. The on-call runbook's first question is always whether anything shipped in the last hour. The fix is process, not topology, staged rollouts that reach a small percentage of the fleet first, a well-rehearsed rollback path, and treating a manual cache flush with the same review rigor as a code deploy, not a one-off command run by hand. None of this matters without a way to detect when it breaks. The service-level objective, 99.9% of redirects complete inside 10 milliseconds, measured over a rolling 28-day window. One alert combination matters more than the rest. If P99 latency rises, the cache hit rate stays flat, and a deploy landed in the last 15 minutes. That's an operator error. The fix is rollback, not scaling anything. The same latency rise with the hit rate dropping instead points at a hotkey or data store health problem, a completely different response. Zoom out, and this isn't really a URL shortener. It's a read-heavy, failure-isolated redirect, a cache-fronted key-value lookup behind a non-enumerable public key. That same shape shows up in paste-to-bin-style paste services, QR code deep link redirectors, and invite or coupon code systems. Only what the resolved value represents changes. Push write throughput hard enough on a single shard, sustained load approaching 256 IDs per shard per second, and the 46-bit ID budget starts to strain, the same ceiling already named as the ID generation decisions migration trigger. It would need to be resplit across timestamp, shard, and sequence bits differently. What doesn't move? Code uniqueness still holds, because a bijective permutation is still a bijection under a different bit allocation. Only the timestamp lifetime versus sequence headroom trade-off changes. Now change the requirements instead of the scale. Enterprise customers start requiring audit logging and data residency guarantees, and two decisions take a real hit. Storage Engine's core premise breaks outright. A write-heavy audit trail on every redirect is exactly the right pressure that decision was built to avoid on the hot path. And failure isolation's assumption of one global failsafe path breaks too, because residency means that path has to be regional, not global. What survives unchanged? Durable mapping and code uniqueness. Those govern where and how data is replicated and audited, not whether a code maps uniquely to a durable destination. A URL shortener isn't a database design problem. It's a caching and non-enumerability problem wearing a database's clothes. Picture a post office lobby with two doors, a staff front desk answering redirects, and a fireproof back door still handing out mail even if the front office burns down. This shape, an obfuscated key, a cache in front of storage, a failure-isolated read path, reappears in pastebin-style services, QR code redirectors, and invite code systems. Only what the resolved value represents changes. Self-test. What flexes under load, cache capacity, and what stays fixed, the record each code resolves to. Before moving on, two questions worth sitting with. What's the weakest assumption this design leans on? That a single viral link draws at most 5% of peak read traffic onto one key. Go materially higher, and cache-based mitigation alone stops being enough. And this design assumes the failsafe read path and the primary stack can genuinely fail independently. What changes if both run on the same cloud provider's infrastructure?